Hello, and welcome to my SpF research overview. My name is Evan Weinman, and I'm a senior at Kean University majoring in information technology and minoring in cybersecurity. I joined our deep learning research group this summer to focus on working to improve and expand Dr. Lee and Professor Kumar's recurrent neural network script. During my time with the research project, I was able to accomplish a number of tasks within the 8 weeks. The first two topics covered will be about the package add-ons MySQL Connector and Matplotlib. Afterwards, I will talk about two papers I wrote going over new discoveries with accuracy versus iteration, as well as the major differences between basic cell and multi-cell LSTMs. This will lead into a deeper dive into multi-cell results between TensorFlow 1 and 2, as well as multi-cell multi-input results. From here, I will talk about the different languages that I successfully connected to the script and the results of testing different languages using the same book, The Raven. Lastly, I will be showing the results of running different text file sizes through the same amount of epoch, as well as running encrypted files through the RNN script. Please take a moment to take a look at the short abbreviation list provided. The first task in the research project was figuring out how to connect our current RNN script to our database so we could start to store the information that the script was providing us. I found a Python driver named MySQL Connector that allows communication between Python and MySQL servers. I was able to call what was on the database into Python and use Python to add new information to the database itself. From there, I was able to alter the RNN script to make a recording into the database after every iteration. During each iteration, it would also record the accuracy and loss. Once we got the RNN script to record some of the information into the database, our goal was to continue to alter the script until we were able to successfully log all the information that was being provided to us after each iteration. This included each inputted word going into the script, as well as the actual expected response and the predicted answer the script was able to make. Other information like submission database and the test ID were added as well to make it easier to sort through the data in the database. I was then tasked with figuring out how to graph the results of the RNN script so that we could easily view both the accuracy over the iteration as well as the loss. Using the library tool Matplotlib, I was able to add a bit of code to the end of the RNN script that plotted the values of the accuracy, loss, and iteration after each iteration of the script completed. Once the script finishes, a new window opens with the graph that was plotted. This tool ended up being extremely useful and something I continued to use and rely on for the rest of the research. Once I finished connecting the graph to the script, I started testing out how accurate the script could be when running different file sizes with the same number of iterations. The results ended up being very interesting and the source of the first paper I wrote for a research study. I compared two text files, one with 8 words and the other with 1,332, both running on 50 iterations and a TensorFlow 1 connected script. With only 50 iterations, it became obvious that the more words that appeared in a text file, the less accurate our script would be with only 50 iterations. As can be observed, the quick brown fox reached 100% accuracy by the 4th iteration, whereas the Declaration of Independence never reached 100% accuracy and only gets 20% accurate within the 50 iterations. Thus, for a TensorFlow 1 script, more iterations are necessary for bigger text files in order to reach 100% accuracy. Previously, our tests on accuracy over iteration were testing different file sizes on a singular basic cell in our RNN script. However, we were able to add multiple LSTM cells to our neural network and were able to garner great results in comparison to the singular cell. I ran our Declaration of Independence script through both basic and multi-cell scripts using 3-word inputs and 50 iterations. The results showed that multi-cell script was able to start gaining higher accuracy quicker, as well as overall achieving a higher accuracy mark 2 times more than the basic cell. The next bit of research I did was to see if changing the amount of inputs that went into the RNN script would change the accuracy we gained within the 50 iterations it ran on. Our basic inputs we had been using were 3 words, so I tested the least amount of words possible with 1, something that was slightly bigger with 6, and then something much bigger with 12. From the results, you can see that 1 input into our script led to very weak results in the 50 iterations, where it only reaches about 8% accuracy. throughout. 6 words ended up bringing us very close to 100% accuracy within the 50 iterations. However, I was able to discover that the higher the input value does not mean the better the results, as the accuracy depreciates at higher input values. Thus, a TensorFlow 1 script running multi-cell LSTM benefits the greatest from 6 input values. Towards the middle of our research, we fully upgraded our RNN script from TensorFlow 1 to TensorFlow 2. From here, I wanted to graph the improvement from our Basic Cell TensorFlow 1 RNN script all the way to our multi-cell TensorFlow 2 script using the same Declaration of Independence script for all 3. As you can see from the graph below, we saw a massive improvement in accuracy when upgrading to TensorFlow 2. Using multiple iterations between epochs led to our 1,332 word script to reach 100% accuracy within 50 epoch run, something that we weren't able to accomplish previously. While the new TensorFlow 2 script was successfully able to reach 100%, I did notice an increase in time it took to completely finish running, going from 23 minutes in a multi-cell TensorFlow 1 script to an hour and 20 minutes in a TensorFlow 2 script. My next step was figuring out how to run different languages through the RNN script and seeing whether the script could predict as well as it does with English within 50 epochs. A basic change in the structure of the script allowed a lot of different languages to appear on a Linux platform. Both Russian and Arabic can be seen below. I continued to try and input different languages into the script to test out the results. As you can see below, I was able to add Chinese, Greek, and Thai. I believe the accuracy in the Chinese script is due to the nature of how our script reads languages. Once I was able to get different languages connected to the RNN script, I tried to see if one of the languages was more accurate than another by running the same Edgar Allan Poe story, The Raven, in English, Spanish, and Russian. It turns out that there is no major difference in accuracy in the end, but Spanish and Russian became more accurate sooner than English. With the old Basic Cell TensorFlow 1 script, we discovered the size of the file greatly affected the accuracy of the RNN script. I decided to run a similar test again with the new TensorFlow 2 script to see if the results would be similar or not. I reused our old Declaration of Independence script and then picked 2 different literatures, Frankenstein and Lord of the Rings Fellowship of the Ring, where the text file would be much larger. As you can see with TensorFlow 2, the file size does not matter at all as the results are similar, once again showing the major improvement that TensorFlow 2 is to TensorFlow 1. The final part of my research was to find out whether we can convert a text file into an encrypted text and then run it through the script to see if any patterns emerge. I started by using the software library OpenSSL, an outdated encryption library for encrypting and sending files. I was able to encrypt the book Frankenstein and convert it into bytes for the RNN script to read. Unfortunately, the data that was being given didn't emerge any sort of useful information on patterns with the encryption. This method was tried again using hash encryption instead of SSL, but led to similar results. I'm currently working with my group on creating a neural network from the ground up that accurately adds 2 numbers as well as multiplies 2 numbers. Overall, we are looking for ways to tune the neural network to make it both faster and accurate to the user, as well as explore what other ways a neural network can be used outside of its current applications. I would like to take a moment to thank Dr. Lee, Professor Kumar, and the rest of the research team for the great collaborations and contributions to this research and the guidance they provided me along the way.